All right, everyone, we are finally at the point where we can describe what a semiconductor looks like, and in particular, what a junction looks like when it's been illuminated. We've sort of been building towards this the entire semester or the entire term. And finally, we have all the information that we need to start really taking apart what goes on in a semiconductor, in a junction, when a photon is incident on it. So what we're going to do is start by thinking about how incident light affects the different types of carriers. So we've been referring to different types of carriers as like electrons or holes, or N-type or P-type carriers. There's a different bit of terminology just called like majority or minority carriers. So majority carriers are whatever is the majority in your semiconductor. So if you're an N-type, it's electrons, it's N-type carriers. If you're P-type, it's holes. That's all that is. It's just a new piece of terminology. So let's think about how light would affect the majority carriers. I'm going to work with an N-type, but again, like always, P-types are just the reverse of this. So we have our band bending diagram. We have a junction, and we're going to have a beam of light come in. I'll switch colors here. Yeah. So we have a beam of light come in, or we have a photon come in, and what happens is we take an electron and we have promoted it up from the valence band to the conduction band. Now, if we look at the concentration of both N and P type carriers in this device, the concentration of N type carriers is pretty high. Right, the concentration of electrons in our conduction band is rather high because it's an N-type semiconductor. It's doped. So when we illuminate it, generally, when you are illuminating things, the photon flux and the absorption coefficient works out such that the concentration of carriers that is generated from the concentration of majority carriers that is generated from the photons is insignificant compared to the concentration of the carriers as a result of just the dopants, right? So that's typically how this works. So typically let's say electrons, let's say this. Let's say the number of electrons from photons is generally much, much less than N sub C, right? So the concentration of electrons in our conduction band, or equivalently, much, much less than ND. So what that means is that we aren't really changing our majority carriers all that much. They are still moving around basically like they were before we shine light on them, which is why we've been talking about this so much. It's actually really important for how these materials behave even under illumination. So if we're not really affecting the majority carrier concentration, that also means that we're not really affecting the way that the equations work, right? It means that the equations governing the carrier motion are more or less unchanged for both illuminated and dark semiconductors. So that means that the IV curve or the ideal diode equation that we derived is still valid here, because remember, the ideal diode equation is going to tell you how carriers are moving at equilibrium. It's going to help you, especially with majority carrier motion, because if you recall, when we were deriving it, we were looking at N sub S and A up here in the conduction band, right? So we're looking at reactions up here. So we're mostly concerned about what's going on up here, not so much concerned about what's going on down here. Okay. But here's what does change: the minority carrier current. So even though our majority carriers are kind of doing what they've always been doing, we can significantly affect the concentration of minority carriers in our systems. And it's all, fortunately for us, it's pretty easy to calculate what what this current might be. So because of the semiconductor liquid junction that we have, or really any semiconductor junction, we have an electric field separating our photogenerated electrons and holes. Now, this is something that's sort of brought up in one of your problem sets, where they say that, and we'll talk about this a little bit more when we get into recombination kinetics, but in general, if you shine a photon, let's say over here, you get, an electron and you get a hole, but because there's no electric field here, there's no way to separate them, they just recombine. They just go back together, release energy as heat, and we get nothing out of it. So we design semiconductors and we design junctions such that effectively all of the light gets absorbed in our depletion region, right there. When we do that, we still get our photo-generated electron and hole, but the electric field that's present there separates them. So it pushes the hole, in this case, over this way, and it pushes the electron over that way. All right. Now, because of this electric field, and usually like the strength of it versus like how quickly things recombine, we can make the approximation that all of the photogenerated electrons and holes are completely separated, and none of them are going to recombine before they move away and before they cause some of this minority carrier current. So since the carriers are separated and collected, the photocurrent, or IPH, or JPH, remember J is just the current density, so that's just I divided by A. So the photocurrent is equivalent to the photon flux absorbed by the semiconductor multiplied by the charge, the fundamental charge. So it's literally just how many photons are you getting, multiply that by the fundamental charge, and there you go. That's what your photocurrent is. So you can directly relate photocurrent to to the number of photons that you absorb. So I've got this expression here saying that it's equal to our photon flux, which I have as psi sub f, multiplied by the inverse of our transmittance, because remember, transmittance is going to be equal to I over I naught. And what we want to know is really, I guess this should be transmittance minus 1. So we want to know the fraction that are absorbed. So let's do that. Let's change this transmittance minus 1, right? So that we have I over I naught. Let's say that the intensity of light on the other side is going to be like 1%. So we get 0.01 I naught. Then we subtract 1. Whoops, we should flip this around. Should be 1 minus. Excuse me. 1 minus t. There we go. And we'll just put a minus there. Add 1. And then we'll get 99.99 as our fraction. All right, so if we have 100 photons incident and we can collect 99% of them, then the photon flux times what we can absorb multiplied by Q is what we get. All right. Now, so the total current that you observe for a device is going to be the sum of the majority carrier current and the minority carrier current. You have to put both of them together. Now, this is true anyway. It's just that typically, like at equilibrium, they're equivalent, right? So they go at the same rate in opposite directions. And we do have to consider as well that the current for minority carriers and the current for majority carriers is going to have opposite sign, right? So if I have electrons going in this direction, this is actually considered negative current if we're considering it to go this way. If we have a hole going this way, that is considered positive current. So we just have to flip that sign. So in expression form, the total current is going to be equal to the majority current plus the minority current. And then we're going to say this is an N-type material. It's doped. So we're going to say the majority is electrons and the minority is holes. And we know from up here that the photocurrent is just equal to the minority carrier. Because the minority carrier current from other sources is insignificant in comparison. We also know from the ideal diode equation that the majority carrier current, the electron current, is going to be equal to, well, the ideal diode equation is going to be equal to our I naught multiplied by our exponential minus QV over KT minus 1. That pretty standard equation that we learned about. Now we're going to put them together. So we end up with the total current being equal to the photocurrent minus, because remember that sign right there, the ideal diode equation. So what this means is that the current that happens, the current that is measured from a semiconductor junction under illumination is equivalent to just the regular diode equation, but offset by a constant. And that constant is the photocurrent, right? So what does that look like? So what that looks like on this graph is this. In the dark, we have our ideal semiconductor behavior here, where we have our current approaching I naught down here. And then it crosses 0 right there. And then it increases exponentially, right? As we get further and further into the negatives, right? This should be current voltage. So this is offset by the photocurrent in all places. Now, I didn't draw it super great, but it's offset by photocurrent here. It's also offset by photocurrent here. It's offset by photocurrent there and there. And again, I'm not doing a great job of drawing this, but I think you get the idea that literally you just take your ideal diode curve and then you just translate it up by an amount equal to the photocurrent. That is what it looks like under the illumination. So this graph looks very similar to the one that we've been interested in, but there's a couple of new points here. So remember, like before, we were interested in I naught, which is what this levels off to down here, right? But now it levels off to something else. Also, we were interested in what happens when there's no voltage, no applied voltage, right? And we knew before that's equilibrium. That means that the current's got to be 0. Well, now the current's not 0. And before, we crossed over from having some positive current to negative current right there when the voltage is 0. But now the crossover is somewhere where the voltage is not equal to 0. So that's interesting. That means that we have to have equal and opposite currents occurring at a point where we are applying a voltage, right? So that means that we are modulating, we're altering the band bending diagrams, and we're moving things effectively out of equilibrium, and yet we're still getting more or less equilibrium behavior. We're getting no current going one way or the other. All right. So these things, these parameters are called the open circuit voltage, the short circuit current, and the maximum power output. That's the other thing that we need to care about, is we can actually figure out, because current times voltage is power, we can figure out the maximum power we get out of this semiconductor. There will be another term called the fill factor that we'll talk about for a minute. That will be a result of the all three of these parameters. Okay, so let's start with open circuit voltage. So the open circuit voltage, or VOC, is the way that I like to say it. Some people, if you go into the literature, will put OCV like this. That's fine. So some people will say OCV in all caps, some will do V sub OC. Either one is fine. You might encounter both. So what it is the maximum free energy that can be extracted from our semiconductor. And an open circuit, what that means is literally, like if you were to take like, all right, so I've got like some wires here. And when they're connected, we make a circuit, right? I've got like a circle going. And so all I'm going to do is disconnect it and measure the potential across these. So for example, if we were doing electronics, so let's say I've got a battery here, and then I've got a switch. Just like so. So if I close this, what I've done is I've shorted the circuit. So what that means is that current is able to flow freely, and we're going to get the maximum amount of current we possibly could. And we're going to say that there's no voltage there. Or what we could do is what we're going to do here, which is we're going to leave the circuit open, which means that there's no current flowing at all, right? Because there's no connection. So there's no way for the electrons to get from here to here. There's just too much space there. They're not going to tunnel through like a couple centimeters of air. And then what we're just going to do is we're going to put a voltmeter on there. We're going to measure what the voltage is. That's sort of what we're doing here. We're measuring what the voltage is when there's no current flowing. Now before, the open circuit voltage was 0, because if there's no current flowing, that means we're at equilibrium, which also means that we're not applying any voltage. But now we can apply voltage and still get to a point where our current is 0. So that's what we're going to do. So let's solve for that. Let's solve for what that looks like. So in the case where the photocurrent is significantly larger than the dark saturation current, or I naught, which is totally normal and a very reasonable assumption, we can approximate the current voltage relationship as such. So all we did is we got rid of that -1, because that would be like minus I naught. And we're saying that's too small for it to matter. So we're just going to simplify it a little bit. Then at open circuit, we define that the current, the total current, this one, is equal to 0. And that the voltage is now equal to our open circuit voltage. So we're going to change that parameter there to a specific value. All right. So we end up with this. We just set everything equal to 0 right over there. And we have our new VOC in there. All right, so what we're going to do is move the photocurrent we're going to move our majority carrier current over to this side of the equation, just like so. We're going to set them equal to each other. Then we're going to take the natural log, end up with this over here, and then solve for VOC. So we get this minus KT over Q, natural log of this. But we're actually going to define VOC is going to be equal to the absolute value of V at I is equal to 0. And so we're just going to get rid of that minus sign right there. And so the VOC, or our open circuit voltage, is going to be equal to KT over Q times the natural log of the photocurrent divided by the dark saturation current. All right. So a couple things to note here. Big voltage is good voltage, right? Because of our relationship, power is equal to current times voltage. If we increase the voltage, we increase the power. More power is more better. So we can note that the VOC is proportional to the natural log of the photocurrent, which means that if we bump up our photocurrent, we must bump up our voltage, which is good. So what that means is that if you have a more effective absorber of light, if you're absorbing more photons at a time, you're going to get a higher voltage, which means you're going to get more power. You can give them more free energy. It's also inversely proportional to the dark saturation current, or that I naught term. So the I naught term, remember, is related. Let me put this out here. So I naught is dependent on the charge transfer coefficient for the electrons, right, across the interface. So if we have a system which has, say, like a lower built-in voltage, or it has just really facile kinetics, which means that things are just able to move really, really easily, we are going to get a larger dark saturation current. And if we have a larger dark saturation current, we have a worse voltage. So what we want for a good voltage is lots of absorbed light and very little current from other sources, especially from like those leaky interactions. All right. The next thing to look at is our short circuit current density, or I'm going to write it as the JSC. It's the ISC. JSC is just ISC divided by the area. I'm more comfortable saying JSC because it's just what I have done for all of this research that I've done. So I would say it anyway. So I just changed our verbiage here. Okay, short circuit current density, JSC. It's important. What is it? It's the current that's flowing when there is no voltage applied. So in our electronics example, we have our battery. And this time we have flipped the switch. We are allowing all of the voltage to flow all at once. And we're going to say, like, go as fast as you can, right? We're going to apply no bias. We're just going to hook up our semiconductor. That's all we're going to do. We're going to put a wire, for example. We have our, let's say our semiconductor. We'll just draw it this way. We have our semiconductor, and we have our liquid, like so. We're literally just going to have a wire that goes between the two. So if there are electrons generated in solution, they can go up and around and then back in. Cool? Okay. All right, so this parameter happens when the applied voltage is 0. So if we plug this into the equation, we're going to just get the photocurrent minus the dark saturation current density multiplied by exponential of this, which is just going to be exponential of 0 because our voltage is 0, minus 1, which exponential of 0 is 1. So we have 1 minus 1, which is 0. And so this whole term just disappears. And the short circuit current density is just equal to our photocurrent. So when we measure our photocurrent, we're really just measuring our short circuit current density and vice versa. And what that tells us is how well our semiconductor absorbs photons. If we have a large current, that means that it's really good at absorbing photons. If we have a small current, that means it's really bad at absorbing photons. So one of the things that's difficult to understand about all of this setup is, what do the band bending diagrams look like under these situations? So what do they look like physically, right? All right, so at equilibrium, we have some rate at which electrons flow, some rate at which holes flow. We know that they are equal and opposite because we have no net current. And we have our equilibrated Fermi level right here, right here. All right. So when we illuminate this semiconductor and we leave it at short circuit, so we are just connecting the wire and we are not applying any voltages at all. We're just letting the current flow. What we're going to see, remember, the concentration of majority carriers doesn't really change. So we don't really affect that rate. What we do change is the concentration of holes down here. And so what's going to happen there is, remember our adage, electrons sink and holes float. Well, if we generate them in our depletion region, the holes are just going to float right out into solution. And because we're increasing the concentration of holes, we are increasing the rate at which they diffuse out into solution. But because we have set up this wire, so these are in electrical contact and there's no bias that we're putting on these things anymore, the Fermi levels are still going to be basically equivalent, right? Because we are providing a method for, we are providing a method for which, under which these things can equilibrate, right? Okay. So that's what we're doing here. The next thing that we're going to do is we are going to apply positive voltage. So the way that this works is now we are going to apply a voltage such that we are going to increase now the rate of our majority carrier motion so that it is equal to our hole carriers. Now, I did realize there is a mistake here. So here's what this is actually going to look like. Yeah, there we go. That's going to look like that. And that's going to look like that. And we are going to have sort of a fake Fermi level down here. Okay, so here's what's happening. Remember before when we were doing, what we were doing is we were changing the concentration of electrons and holes in the conduction or valence band based on the number of dopants, right? And doing that modulates where the Fermi level is. So I was wrong before to say that the Fermi level is equilibrated. This is incorrect. In fact, what happens is your Fermi level is going to go down a smidge because you have increased the concentration of holes down here. So remember, the Fermi level tells you when there's like a 50-50 shot of finding one or the other. So if we've got like a whole bunch over here and say like a whole bunch over here, it starts out, the Fermi level is like, say, there. And then we're going to increase this. So now the Fermi level is going to come down right there. Okay. So that's what's going to happen there. So we're going to get this separation here. Now we're actually going to get a separation equal to VOC. At open circuit, or at actually at closed circuit, we're going to get a separation equal to VOC, because then what we do is we apply this voltage and we're going to keep applying it until our Fermi levels equilibrate. And when our Fermi levels equilibrate, that means we have equal electrochemical potential on either side, which means we have no net reaction. And if we have no net reaction, that means the current is zero. So that's what's going on there. And notice the bands are unbent to make it easier for the electrons to move. In fact, hypothetically speaking, you can unbend them to the point that they're flat. So there is actually something called the flat band potential, BFB, which can be like subtly different from the VOC, but effectively same idea. And so what you're going to do is you're going to apply a potential, and you're going to push the bands back up or down if you're doing p-types. You're going to unbend your bands until you have compensated for the VOC that we generated there. And we are now flowing electrons just as fast as we're flowing holes, which means no net reaction, which means no net current. That's what happens at JSC. So you can see this is very confusing. It's very confusing to me. This is one of the things that I have the hardest time understanding. But this is what it looks like. All right. Now we're going to think about power. So power is defined as, like we mentioned before, current times voltage. So if we use an IV curve and we multiply the current and the voltage at each point, we get a relationship that looks like this. So the power is going to steadily increase until we hit some point, say like around there, and then it's going to decrease, right? Because our current is going down here, even though our voltage is going up. And so the power itself is going to be going down. So the maximum power is, wherever we get the max value. So it's like right about there, which would be, if I go straight up, that point right there. And usually it's drawn on the curve kind of like this. We call that P max. Now, hypothetically, the best power output that we could expect from our semiconductor is going to be our JSC or our ISC multiplied by our VOC. So we are going to set that as like the ideal, right? We can't get there because of the way the ideal diode equation works, but like you could imagine it would be kind of nice if we just had like our I and our V, and this is our VOC, and this is our ISC, and the curve just kind of looked like that. It was just literally a square. And then we would get our maximum power right there. Unfortunately, that's not how it works. And so what we do is we compare P max, wherever it may be on our curve, but we're going to get that value, and we are going to compare it to this hypothetical maximum value to get what we call the fill factor. Think of it as like the fraction of this hypothetical square that is filled. So like all of this is filled, but hypothetically all of this should be filled too. So the fraction that is actually filled is going to be the fill factor. And it's just equal to P max divided by JSC times VOC. It's going to be really important as we discuss ideality. So I've been talking about ideal semiconductors, which have these, these beautiful, these beautiful curves that look just like this. But a real semiconductor can sometimes look like this, or like, say, this. And so in this case, our fill factor might be like right there. Our P max might be there, which would be a very bad fill factor, right? Compared to the size of this box to the IV box. So it helps give you an idea of how ideal your semiconductor is. Then we care about the efficiency, right? That's the number everyone cares about. How efficient is your solar cell? Now, Nate likes to go into this whole sort of rant about how different people calculate efficiencies in different ways, and sometimes people calculate efficiency incorrectly, and especially for thinking about photoelectrosynthesis cells, where we can say like, okay, well, is the efficiency like the electricity we get out, or is it the free energy of our products? But we're just going to simplify it and say we're going to do this purely photovoltaically, And the efficiency of our solar cell is the power extracted at our maximum power divided by the power that's input. So usually this is just, all it is the incident light intensity. So the efficiency is just going to be equal to the maximum of I times V divided by our power in, which is just this, right? Which is our power in. So remember, if you're looking at solar energy, it's like on the order of 100 milliwatts per square centimeter. Then divide that by 100. Or sorry, multiply that by 100 because we want percent, right? This is going to be efficiency as a percent. Equivalently, since we know that the fill factor is going to be equal to P max over, say, ISC times VOC, we can just multiply this over and substitute that for this guy right there and say that the efficiency is going to be equal to our ISC, our short circuit current, our short circuit current multiplied by our open circuit voltage multiplied by our fill factor divided by our input power. So in order to maximize solar cell efficiency, what do we want? We want a high voltage. And the way that we get a high voltage is by getting small dark saturation current or a bad KET. So what we want is, if you remember from when we derived the ideal diode equation, we could either get a big barrier height and get like really good VBI, because if we have a large built-in voltage, we can have a small I naught, or we can have a system that has really bad electron transfer kinetics. And so we have a bad KET, a bad constant for the electron transfer rate, or both. Really, what we would like is both. We want to get this voltage as high as possible. And we also want a really high short circuit current density, which means we want a really high photocurrent. So we want something that absorbs really well. Plus, we want it to have a good fill factor, so we want it to be as ideal as possible. So we want something that is as close to ideal of a semiconductor as possible. We want it to have a really good built-in voltage, and if we can swing it, and really favorable electron transfer kinetics. We also want it to absorb as much light as possible. And if we do that, we will maximize the efficiency of our solar cells. So that is how solar cells extract power from light. That's how we generate photocurrents and how we use photocurrents to generate power. And so in the next couple lectures, we're going to get into things like recombination kinetics, and then we'll look into some applications. So I'll see you on the next lecture.